Hi everybody, and welcome to module number 4, which is on physical geography. Last module we went over physical geography also, but we were looking more at like geology and kind of earth structure and the things that go on in the earth. On this section we're looking at weather and climate, which is another thing that geographers like to look at to try and understand why certain places are the way they are in the world and why there's a difference in terms of weather and climate across the world. So the four main points we're going to get into today is first we're going to talk about the way in which energy comes into the atmosphere, mostly from the sun, and how that drives how the atmosphere circulates, and therefore why some places are, have a dry climate and some places have a wet climate and all of that kind of stuff. So again, start first with the discussion of how that energy enters the atmosphere. Then we'll talk about then the general model for how the atmosphere circulates. There's some good kind of general rules of thumb that gives us an idea of why certain places have the kinds of weather and climate that they do. And then we're going to look at one of the ways in which precipitation is made, particularly here in New England, which is fronts. We're going to look at like cold fronts and warm fronts. And then we'll talk a little bit about climates and how they relate to biomes, which is discussed in the chapter, but biomes being basically kind of the different kinds of environments that we find around the world, like rainforest or desert or that kind of stuff. Okay, so jumping right in, the first main point has to do with the way in which energy comes into the atmosphere. As you probably already know, different parts of the world are warmer than others, right? Everyone knows that the tropics get a lot of, are very warm, it rains a lot, you have these rainforests, whereas you have other parts of the world that are deserts, and then you have other parts of the world like the poles, which are very, very cold. Well, this gets into a little bit about why that is. Okay, so first, if we look at the general kind of energy budget of the Earth and its atmosphere, we get most of our, last week we talked a little bit about, or last section we talked a little bit about how a lot of the processes around geology are from the heat that's within the core of the Earth, right, that kind of drives the plates moving and all of that. Well, in the atmosphere, it's almost all coming from the sun. So you get all of this incoming solar radiation, and what happens to it is about 30% of it gets reflected right back into space, mostly from the atmosphere, but some from the surface of the Earth, particularly places where there's a lot of ice. That energy just gets reflected right back. Some of the stuff that does reach the Earth, right, it says here 45% is absorbed by Earth at the surface. So a little less than half of the incoming solar energy comes in and hits the Earth. And then some of this other part of this energy gets absorbed by the atmosphere. Then what happens is after that energy hits the Earth, it gets re-radiated back up into space. However, as you can see here, it says about 70% of the heat that the Earth generates is lost to space. Sorry, this kind of is behind me here, but there's an arrow coming down this way that shows that about 30% of that heat actually isn't lost to space. Instead, you have things in the atmosphere like carbon dioxide, methane, and other gases that hold some of that heat in. And this is what's referred to as the greenhouse effect. Without this effect, the Earth would be a much, much colder place. And this does have, is a natural component of the Earth's atmosphere. When we talk about climate change, and like they do in the book, talk about climate change, it's not so much that there shouldn't be any greenhouse effect. It's the fact that the greenhouse effect is becoming enhanced because we're putting more of these warming gases into the atmosphere, which traps more and more of this heat, so we're losing less heat to space. Now, one of the reasons why it works like a greenhouse is, I'm going to just change this for a second here so we can see it a little better because it's hiding behind my face, is that this is showing the electromagnetic spectrum. Now, sunlight, when it comes in to hit the Earth, or any kind of energy, operates in different wavelengths. Most of the sun's energy that is coming and hitting the planet, it really is in this visible spectrum here shown between purple and red. So most of the sun's energy is coming through in that wavelength, and that wavelength, most of the particles in the atmosphere are transparent to that wavelength. In other words, that's why most of the energy is getting all the way down to the surface. However, when the heat is re-radiated by the Earth and it goes up back towards the atmosphere or towards into space, it doesn't re-radiate at the same wavelengths. Instead, it is way over here in the infrared part of the spectrum, and so this is kind of showing that part of the spectrum that goes everywhere from cosmic rays and gamma rays down to like radio waves. And over here, these waves are essentially much shorter wavelengths, higher energy, and out here, longer wavelengths and less energy. So you have this other kind of radiation being put back into the from the Earth to the atmosphere. And this is why the CO2 and other things act as a greenhouse effect. They don't block, like CO2 doesn't block this energy or absorb these wavelengths. Instead, it absorbs down here in this wavelength, and that's pretty typical that different types of chemicals or molecules absorb energy at particular wavelengths. And so because of that, the CO2 allows the sun's energy to come in, and it doesn't absorb it then, but after it hits the Earth and gets re-radiated, it does absorb it at that point. And so because of that, so that's where you get the analogy to a greenhouse. Think about it for a second in terms of like a car, or your car on a hot day. The panes of glass that you have on, like for your windows, they let the sunlight in, right? In those wavelengths, it's transparent. However, the heat energy that is then generated when that sunlight hits your car seat, let's say your car seats are black, makes them nice and hot, that energy that's being re-radiated back out from them, the glass actually traps those wavelengths, and so therefore you get this buildup of heat that gets more and more and more intense inside the car. Essentially the same thing is happening at the whole level of the atmosphere. Okay. So that's one aspect of the atmosphere and how it affects climate. The other thing is that not all parts of the Earth get the same amount of solar radiation. So when the sun is directly overhead, and those of you who, like, well, in the summertime here in New England, when the sun is directly overhead, or not, excuse me, it's never directly overhead, but because of the tilt of the Earth, which I'll get to here in a second, during the summer, the sun is closer to being overhead than it is in the winter, right? In the winter, it's far on the southern horizon, and so we're not getting as much energy. And here's why. Well, so that's one thing about seasons, but also when we look at the planet about the tropics versus the poles, it also has to do with the angle at which that sunlight is hitting. So think about it this way. If the sun is over here and is very large, and you can think of all of the sunlight coming from the sun as essentially aiming towards the planet in parallel lines. And let's say you've got like a square meter of sunlight kind of flying towards the Earth, and it hits. If it hits here, all of that sunlight is concentrated in this one square when it hits directly overhead. If, however, the sunlight is coming at the pole here, that same square meter of sunlight sort of gets smeared over a much larger area because of the angle at which it's hitting the ground, or hitting the Earth in this case. And so that same amount of energy is diffused over a larger area. So if we look at it like this, if the sun's directly overhead, you have this 90-degree angle. All the sun's energy is very compact and packed into a small area. And of course, there's more sunlight next to it also doing the same thing. If, however, that sunlight comes in at a very sharp angle, that same amount of energy gets spread over a much larger space, and therefore each individual kind of square meter on the ground is receiving much less energy. All right. So because of this, it means that the tropics here are getting about 2.5 times more energy than the poles, just because of the way in which the sunlight is hitting those angles of the Earth, of the spherical Earth. But of course, it's a little bit more complex than this. This example here, where it shows the sun directly over the equator, is a situation that only happens during the equinoxes, right? We know that there are seasons, and what that means is, during the seasons, is that the point at which the sun is directly overhead moves north in the summer and south in our winter. So for instance, in June, the sun is almost directly overhead here at what's called the Tropic of Cancer. It gets directly overhead on that date, and so because of that, that means places in the northern hemisphere, like us here in North America, have a much more, the higher sun angle, and so we're getting more energy. Whereas during that same time period, you get winter in the southern hemisphere because the energy is not coming, it's coming in at essentially more of an oblique angle. Then when you get down to December, the sun is directly overhead over what's called the Tropic of Capricorn in the southern hemisphere, so places like Chile and Argentina and Africa are getting much more direct sunlight and are warmer, and then that's when we have our winter. And the reason why it's colder is because, again, the sun's further south, so it's coming at us at a more oblique angle, and therefore we're not getting as much energy from the sun during that time period. So the reasons for that tilt, and you can see this in the book too, it gives a fuller explanation, has to do with the fact that the Earth's axis is tilted, but it's tilted in a way that is constant. So for instance, if there was something on the ceiling, let me see here, use it like this example, let me use this hand, that way. Okay, so the Earth's North Pole is always aimed at this point in space where the North Star, Polaris, is, and so if my head is the sun, if it's over here, you can see that the sunlight that comes from the sun is going to hit the northern hemisphere, or excuse me, the southern hemisphere more directly, right? Because the southern hemisphere is going to aim towards it. As it goes around the sun and comes around to this side, this point of the year, you can see the angle didn't change. It's still pointed the same way, but its relationship to the sun is different. And so now the northern hemisphere is the one that's more directly pointed at the sun. And so that is what explains why that sun appears to go from, move north and south, has to do with the way in which that constant angle of the Earth as it goes around the sun makes different north and south parts of the Earth point at the sun more directly during different times of the year. Sometimes that can be hard to visualize. There are some places online you can find some visualizations that might help with that. Okay, and then as we pretty much know, this is a isoline map, which we talked about different types of map back in one of the earlier modules. Isoline maps are maps where everything on a particular line is the same, and so on this is showing the case in the northern hemisphere winter, and what these lines mean is if you look at the 70° Fahrenheit, it means all the temperatures average 70 degrees on this whole line. So it means that if you're on this line, that means the average temperatures are 50 degrees during the winter on this whole line. You can see places like Siberia obviously have like -20, -30, -40 during the winter, right? Pretty dramatic. Whereas in the summer, that flips around and you actually have relatively warm temperatures over Siberia and you get the colder temperatures than over places like Antarctica. Okay, so one of the other things that then happens with this incoming energy is that it gets transferred through the atmosphere. So in other words, you're getting parts of the world at any given time are getting much more energy than other parts. And the Earth, just like most systems, doesn't like it to have a lot of heat built up in one area and not a lot somewhere else. What's going to happen is that heat that's generating down here is going to find a way to essentially move up to the areas where there's less energy. And so a lot of what's going on with atmospheric circulation has to do with moving that energy around. And there are basically three main ways in which that heat is moved. One is conduction, convection, and the other is, well, excuse me, three. Conduction, convection, and radiation. Conduction is when heat is transferred from one place to another strictly by things being in contact. And I'll show some examples of this. Convection is where you actually are moving heat by moving the fluid or the air that is that warmer temperature. And that's a lot of what's going on in the atmosphere, is that you're having air that's warmer here moving to where air is colder. And it creates what's called a convection cell, which I'll talk about here in a second. And then the last is radiation, where you just are getting electromagnetic radiation, kind of like I talked about in terms of the way in which the solar energy gets to the Earth and also the way in which the heat energy from the Earth gets back out. So here's a good kind of illustrated example, which is this is conduction. So pretend that you are cooking water over a stove and you have radiation, which is here's your burner. You can hold the pot above the burner and you're still going to feel heat, right, going through the air. That's radiation. That's one way of moving heat. The second is conduction. The pan gets hot. That makes the metal of the handle gets hot, and if you're not wearing a hot pad, that heat moves all the way to your hand and you feel it, right? The other kind of way that the heat moves is that if you boil this water down here, it sets up what's called convection cells, which is that the water heats up here at the bottom, that then moves to where the water's cooler at the top, that colder water then sinks, and you start getting these cells of water movement essentially going on in the water. And this is going to be very critical when we talk about the atmosphere, because a lot of what's going on in terms of heat transfer in the Earth is by convection. The last form which you'll see here is called latent heat. And let me discuss this for a second. Right. Latent heat is a little different. Sensible heat transfer is heat that can be measured with a thermometer, and so all those things like radiation, conduction, convection has to do with the movement of that sensible heat. Latent heat is a little bit tricky. That's the energy necessary to cause a change in state of a substance. So usually we're talking about water. Sorry, I made it small here so you can see it behind my picture. So latent heat is the energy necessary to cause a change in state, and that means things like turning, like with water, it's turning something from ice to water, or from water to water vapor. All right, and so what happens with latent heat is that when you have water being evaporated from the ocean, you have to put in a certain amount of energy to get that water a little bit warmer, a little bit warmer, a little bit warmer. But when it gets to the point where it's about to evaporate, you have to put a whole ton of water in, or excuse me, a whole ton of energy in without changing its temperature just to get it to change state. Same thing with an ice cube. If you want an ice cube and you want to change it to water, to liquid water, you have to add energy, add energy, add energy, and say at first you might have the temperature of that ice cube, right, which changes at 32 degrees Fahrenheit. Let's say the ice is at 20 degrees. You add energy, it goes to 21, 22, 23, whatever. Gets up to 32 degrees, and it's just about ready to melt. You actually have to put in a ton more energy just to make it change from ice to water. So this is important because in the atmosphere, what happens is that when the sun is over an ocean and it's evaporating everything, it has to take a lot of energy to make that transfer. And then when that water vapor is in the atmosphere, it moves somewhere else and then it rains, it actually releases a ton of energy when it changes from water vapor to liquid water. Just like if you have liquid water and it turns to ice, it also releases a ton of energy at that point too. So that latent heat is another way of of moving energy around the Earth. As you get things evaporating near the tropics and you bring that moisture up to the colder areas and making it rain, it is one way of moving heat around, and an important one. Okay, so that was the main point number one. These other ones should go hopefully a little bit quicker. Main point number two is the general circulation of the atmosphere. And this, sorry, it says on a page number here, and I don't believe that's the right page for the book. This is the general model for how the winds move around the Earth. And this is a very critical idea because how it works is like this. The equator here, if we assume that this is where the sun is most directly overhead, which it is a good chunk of the year, right, as we know from season that moves around. But if we take this example here at the equator, so the sun's here. This is the place that's essentially warmest or getting the most energy on the planet. And what happens is, and this is where there's two key things you have to realize about the way the atmosphere works. One is that if you heat air a lot, it will rise up. So you heat it, it will rise. It becomes less dense, it rises up. Just like in our example with the water boiling. You heat something, it will rise and become less dense and move upward. The other thing that you need to know is that as you move that upward, it will cool down, right? Most people know that as you go up to the top of a mountain, it's colder up at the top of a mountain than it is at the bottom or in a valley, right? You go up in elevation, it's colder. So as that moves up, it cools. The third thing you need to know is that when air cools, if it has water vapor in it, it will essentially, the best way to think about this is that as an air mass cools, it can't hold as much water vapor, and so it starts to condense and come out as precipitation. So here in this area, right where the sun is directly overhead, is an area they call it the Intertropical Convergence Zone, or ITCZ. The Intertropical Convergence Zone is this area where there's most of the sun's energy is hitting. It causes the air to go up, and as the air goes up, it gets colder, and it's usually because it's over the ocean, particularly where it's over the oceans, but even when it's over like rainforest areas here, it's really moist air. As it cools down, it can't hold that moisture, and it rains. And so along this line of the Intertropical Convergence Zone is where most of the world's rainforests are. You get a tremendous amount of rainfall in this area, and this is kind of shown here. So the air essentially rises up, rains out, and then the air comes this way and then descends again. The other thing to know then is that, okay, as this air moves around, you have this air that was pretty moist, you moved it up and you cooled it, so it rained, so it lost a lot of its moisture. Now it's fairly dry air coming around, and as it comes back down again, as it sinks, right, if air as it goes up gets colder, air as it goes down gets warmer. And also you have fairly dry air, and because it's getting warmer and warmer, it actually has the ability to hold more moisture in it. So in other words, it doesn't want to release whatever moisture it does have. The take-home story then here is that in these areas, what you get is very, very dry air that's descending. These areas here, what are sometimes called the subtropical highs, are where most of the deserts of the world are. So this line here doesn't do it justice because it's actually a little bit further north. But if you look at like the deserts of northern Mexico or Arizona, look at the Sahara Desert, the Kalahari Desert, the Great Australian Desert. These are all around these subtropical highs. Let me see if I think I've got another, here we go, another good map here. So you get this area around the whole world with the intertropical convergence zone where you get a lot of rainfall and rainforests. And then you get these places of high pressure, which are the deserts at about 30 degrees latitude north and south, right? So southern Africa and the Sahara, the deserts up here in parts of western China, the deserts of Australia, etc. Now then in the areas, if we go north and south of those deserts, we get into areas that are called the westerly winds. And essentially what happens is that the air descends here. If the air descends and hits something, it's got to go somewhere. So where it does is it kind of diverges. Some of it goes back to the equator to kind of set up these cycles here, which are called Hadley cells. Sorry, they got a little cut off here on the video, but Hadley cells. And then the other parts of that wind basically go north this way. And this sets up what's called the westerly winds, which go across, like what we experience here in North America, mostly are the westerly winds. Here in New England, if you want to know what the weather is going to be like in a day, all you have to do is look down this way, right? Like whatever the weather is over places like Chicago or Michigan or Ohio is going to probably get to us the next day. And if you watch some things like the Weather Channel, storm systems usually go from Seattle to the Rockies, across the Great Plains, and over to where we are. And that's because we're in a part of the world where the wind basically follows these green arrows. Whereas if you go to the tropics, the winds are usually coming from the east. It's the opposite. And that has to do with the way in which the wind returns out of these subtropical highs. The very last piece of the puzzle is at the poles. These are areas where there's not much solar radiation, right? So you don't have a lot of energy. You have very cold air. And that cold air is not, because there's not getting a lot of energy, it's not being forced upward. Instead, it tends to just sort of sink. As that air sinks, well, two things. One is that you have very cold air. It doesn't have a lot of moisture in it. It's descending air, so it's warming a little as it descends. Not a lot, because it's such cold air to begin with. But it actually means that at places like the North Pole and South Pole are actually very, very dry. Even though there's a lot of ice here, the rate at which it accumulates is very little. Antarctica is essentially a desert. Most of the places there get less than 2 inches of precipitation per year. And so you get these dry areas on both the north and the south, but very cold. And then the last piece here is what's called the polar front. And it's important for us here in New England because it affects us a lot. This is where these winds that are coming down from the pole meet these winds coming out from these high pressure areas, these westerly winds, and you end up with this little squiggly line around the world where these two wind things are coming together. And when they come together, what happens is that that wind has to go somewhere, and it can't go into the earth, right? And so what it does is as they hit each other, they go up. And as we discussed, as air masses get pushed upward, particularly these westerlies, which have some moisture in them, as they get pushed up, it rains. And what this means is that you get this band around this area of the earth and around this area down here too, where you get a lot of rainfall because you have what's called the polar front. And we're going to talk about fronts here in a second, which will explain why you get so much precipitation, and it's what's responsible for most of our precipitation here in New England. Okay. So this is just a satellite image showing this is the intertropical convergence zone. This is a radar image. You can actually see the line across the world of where all these big thunderstorms are going on. Okay, now one thing I'll say too is I didn't get too much talking about the Coriolis effect, which has to do with why winds tend to turn towards the east or the west in different areas, but there is some discussion of that in the book. So if you're a little unclear as to why these winds come out and kind of spiral the way that they do. You have to look into the book around some of the discussion of Coriolis effect. Okay. Main point number 3, cold and warm fronts. When we think of air, we don't usually think of it as being very stable. We think of it as something that can move around. Like if you have one thing of air over here and one thing of air over here, and I squish them together, it's just air, right? So it just mixes. However, if you get a large, what's called a mass of air somewhere that has similar characteristics, it kind of tends to act almost like a little blob of jello. When it hits another parcel of air that has different characteristics, they don't actually mix all that well. And so when we talk about fronts and we talk about cold air masses and warm air masses, you have to realize that sometimes these air masses don't tend to mix very well when they have different things or different characteristics. Okay, so it says here, air masses do not mix, and fronts are the boundary between cooler and warmer air masses. And the terms here are, that we're probably most familiar with is cold front and warm front. A cold front is when cold air is moving into warm air. Warm front when warm air is moving into cold air. A stationary front is when basically they're kind of moving side by side next to each other, and then occluded has to do when it gets a little more complex. I probably won't, you're not responsible for having to know about occluded fronts, but there is some discussion in the textbook about it. So here's our general diagram. So this is a cold front, and this is what we see most of the time here in New England. You have a cold air mass that's coming from the more polar regions that's moving down into the warmer air masses that you find in the in this area of the westerlies in between the deserts and the polar front. So basically what happens is that you have this cold air mass, and it's essentially moving almost like a bulldozer into the warmer air. And so what's going on with this, I'll try it this way. What's going on with this is as this is going in, it's pushing the warm air up over the top of it. This is what's causing the air to move upward. Then, just like we've seen every time we make air move up, it starts to rain out. And so when you have a front like this and you get this air being pushed up, then you get rain. Similarly, when you have warm air mass moving into a cold air mass, you get the same thing, except that because the cold air tends to be the one that's sunken, and the warm air will go over the top of it. It looks a little different in terms of the way the front kind of looks, but it's the same idea in that you have the warmer air being pushed up, 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 which means that whatever moisture it has in it will start to condense and then rain out. So the difference here is that in a cold front, usually it's a more intense rainfall, but over a shorter space, whereas on a warm front, it's a less intense rainfall, but over a larger area. And here in New England, we will get both of these kinds of fronts. So this diagram here from the textbook can be a little helpful, I think, showing what a typical storm system coming across the U.S. will look like. You have the warmer air here, like over the south, moving into the colder air in the north, and that's creating a warm front where the warm air is riding over the top, so you get a lot of raininess here. You get the cold front, where you get the colder air that had come down from this area plowing into the warmer air, and so you get intense precipitation along this front as well. What will often happen is that this cold front will sometimes catch up with the warm front, and that's where you get what's called an occluded front, but you don't have to worry about that. Okay, so the basic take-home story then on precipitation and things like that is that basically when you get precipitation when you move air up. Fronts are one way to do this, but there are a couple others which you need to be aware of. One of them is from convection. Sometimes if you have warm air, like at the intertropical convergence zone, you just warm it up, which makes it move up by like incoming solar radiation, heats it, moves it up. You can get rainfall that way. That's called convection, and it's what usually creates thunderstorms. You can also get what's called orographic precipitation. Orographic is when you're just taking air and, like, let's say you've got a mountain in the way. The air hits that mountain and it has to go up because it's hitting a mountain. You also get a lot of rain then on that side of the mountain, and that's called orographic precipitation. Also, when the air goes up over the mountain, comes down the other side, you get what's sometimes called a rain shadow. And a rain shadow is just a place where you don't get a lot of precipitation because of it being rained out on the other side of the mountain. So in the textbook and in the rest of the PowerPoint, there are some important examples of the hazards associated with these different types of weather phenomenon, like tornadoes, hurricanes, lightning, etc. Make sure that you are looking at those. Blizzards, that kind of thing. All right, but in the interest of time, I'm going to go on to main point number 4, which is about climate and biomes. First of all, climate is different from weather. Climate is essentially the long-term averages of the kind of weather that occurs in a particular place. And then, so that's what we mean by climate. And then there's another term, which is biome. And biome is the kind of environment you get from a certain climate. So in other words, you know, you would say something about a climate is an area that might be warm and wet, like, you know, it has very warm temperatures, like in the tropics. That's the climate. The biome is tropical rainforest. That's the kind of plants, that's the kind of ecology you get in that very warm, wet climate. And so in the book they kind of talk about this, and so this is a precipitation map of the world. And as you can see, here's the effect of the intertropical convergence zone. You can see places that get a lot of rainfall because of the polar front up here. You can also see where the deserts are, right, in the very light colored areas that have very little precipitation. That map's very, and then what geographers have done is they then kind of give these different climate types that you find in different places these different names. And this is the Köppen climate system, where they'll say, okay, A climates are like the warm kind of tropical ones, B climates are the deserts, C are mid-latitude climates like the American South or Europe, and then you get D climates, which are kind of a little bit colder, which you get up here like in New England, we're a D climate, or like Russia or Scandinavia. And then E's are polar climates. They have a special thing here, H for highland, just showing that places that have very, very high elevation, like the Andes or the Himalayas, kind of have some different type of climates that are have much more to do with their elevation than kind of their latitude. Right? But if you look at the different ecologies of the world, it follows very close to these kinds of climates. So, you know, if you look at where we're going to get you know, forest and, you know, particularly tropical forest, that kind of stuff, it's going to be where you have the tropical type of climate. And one of the ways that geographers will discuss these biomes or kind of describe them is through these kinds of diagrams here. And what this is showing, and there's a lot of these in the book, is gives you basically a climate graph for a particular place. So this is an example from Cairo, Egypt, which is similar to places like other desert areas like the southwestern United States, northern Mexico, etc. These up here are the months: January, February, March, April, May, June, July, August, etc. And these bars show the difference between kind of daytime and nighttime temperatures typically, or the kind of range you're going to find in temperatures throughout that month. So for instance, in Cairo, in April, you're going to get temperatures everywhere from about, looks like about 85 degrees to about 55 degrees. Down here is showing precipitation, and over here is the graph for that, showing that every month you're getting less than an inch of precipitation, and in some parts of the year you're not getting any precipitation really at all. So this is what gives you that desert climate. Contrast that, let's see, do I have a tropical rainforest? Nope. Let's take a temperate broadleaf forest, which is sort of what we have here. So this is an example from Chicago, Illinois. You can see that their temperature changes much more over the course of a year, right? Where you have very cold temperatures in January and December and very warm temperatures here in the summer, but not as much change from day to night any given time of year. But precipitation-wise, they have, you know, about 4 inches, or between 2 and 4 inches of precipitation each month, with a little bit more in the summers. And what you get when you get that kind of a precipitation and temperature situation, this is the kind of forest you get: a broadleaf forest, oaks, maples, that kind of thing. So there are other kinds of climates, of course, too. This is a grassland climate. It looks like the example here is from Iran, but places like Salt Lake City, other ones like that, have this kind of climate, which is a little more dry than what we saw for Chicago. The temperature swings are pretty severe still, right? Pretty warm in the summer, still pretty cold in the winter, and that gives you this kind of landscape. Another interesting example here is what's called Mediterranean shrubland. This example for this would be like California. This example here is from San Francisco, and also this is one from Spain. This one's a little different in that the temperature is shown as a line instead of as blocks. But the precipitation here shows that you have some precipitation. Excuse me. You have some precipitation, but mostly in the winter times and almost none in the summer, and that gives you a particular kind of biome, a particular kind of ecology. And then this is like the coniferous forest, so like the forest that you get up in like northern Canada, or this example here is from Moscow, where you have a lot of variation from of temperature, and you can see that in the winter you're very, very cold, you know, getting temperatures down here averaging around 10 degrees, but still a fair amount of precipitation, and the kind of ecology you end up getting is like more of a pine needle, you know, coniferous forest. Okay, so that's the end of the key points for today. I know there was a decent amount of stuff here, but I think it's important to try and explain some of those more complex, you know, some of the more complex concepts around atmosphere and the way that it works. So be sure that you read the rest of the chapter, read the whole chapter, check out the rest of the PowerPoint, and also watch the short video that describes how El Nino works. That's very critical. So that's it, and I will see you next on the next module. Thank you.